So far, what we've looked at are the forces that act on moving charges and current carrying wires. We talked a little bit at the start by the fact that all magnetic fields are created by moving charges. In this case, electrons that are spinning are creating magnetic fields. So we're going to dig a little deeper into how do we know how big the magnetic field actually is. What's the strength? Where is it pointing for the different types of sources that we can have? So we talked about the fact that spinning electrons can create magnetic fields. So you have magnetic fields created by electrons that spin in opposite directions. But this is really based on angular momentum. And you can have angular momentum without actually spinning. So the spinning idea is actually misleading. Any moving charge creates a magnetic field. So for example, here we have a positive charge that is moving in a straight line. So it's not spinning, it's just moving in a straight line. What ends up happening is that moving charge creates a magnetic field, and that magnetic field loops around so that at any one point from that charge you are going to have a magnetic field, and that magnetic field is going to be dependent on the radius. So here we've got like a point. If I wanted to find the magnetic field at that point, it would be based on this radius r. If I were to choose a point that's further away, well, that R is bigger. And of course, if you're farther from the source of the magnetic field, then you're going to have a weaker field. There is something kind of interesting going on here, and that is if you notice along the central axis, if you were on the axis right here of where that velocity is, if I was to pick a point here and draw an R vector, if your R is parallel to your velocity, then there is no magnetic field at that location. So this is going to be based on another cross product. If R is perpendicular to V, then our magnetic field is going to be at a maximum. If you're at some angle between parallel and perpendicular, then it's going to be weaker. It's going to be somewhere between 0 and whatever that maximum value is. So if you were to look in this image over here on the right, there's an X right here. That represents that the charged particle is moving into the page. So if you're looking down on the charged particle that is moving straight down into this page, then there is a magnetic field that's being created that is actually perfect loops. And if I was to look at any particular location, the magnetic field vector at that instant is going to be tangent to that magnetic field. Now notice that my charged particle is going into the page, and I'm making a loop that is in the clockwise direction. If that charge was coming out of the page, it's going to create loops in the opposite direction. So it's going to be important to understand the shapes that are made by these different charges and the directions that they move. So this is kind of a fun simulation. So this website is Falstad. I think I showed electric fields with this website before. In this case, we're looking at different magnetic fields. So if I look at a moving charge, that moving charge is given a direction. So I can see that this one is moving in a straight line. And what's currently being shown are velocities of particles. Instead of looking at that, we're going to look at the field vectors. So if I look at the field vectors, I can see that those field vectors are creating loops. That there are loops that are being created here. And if I were to draw the field lines, those field lines are also making loops. But you can see that if I was to increase our field, I could draw lots and lots and lots of field lines. Okay, so our magnetic field is creating loops. But what is true is along that central axis, there is absolutely no magnetic field along that central axis. I'm not sure there's a good way to show that. Don't know that one. I guess you can kind of see here that there is actually a little black hole that's directly behind the charge. And that's because there's no magnetic field directly along that central axis. So as I mentioned, the magnetic field is going to be stronger closer to the charge. But also the faster the particle moves, the stronger the magnetic field is going to be. And the magnetic field is 0 along the axis that is parallel to the velocity of the particle. On the right, what we can see is that they're kind of showing these larger loops. That's really just kind of showing that you have a stronger magnetic field if you're close to the charge. And over here, they're showing weaker magnetic fields if you're further along the charge. So if you're on this location that is basically at that cross section of where that charge is, you're going to have the strongest field. And remember, along that central axis, there's going to be no magnetic field. So how do you determine the direction? So there is a new right-hand rule. So with this right-hand rule, it's nice and easy. All you do is, if it's a positive charge, you put your thumb in the direction of velocity and then curl your fingers, and that is the direction the field loops. So I can see that here with the hand. So if I put my thumb to the right, then I'm getting loops that are going in the clockwise direction. I can see that in this top-down view. If my charge is going into the page, then when I put my thumb directly into the page, then I'm getting this curling clockwise rotation on that. So from either view, I'm getting a clockwise rotation. Now, remember that negative means opposite. So if we had a negative charge, that negative charge, you'd either use your left hand. So if it's a negative charge, we would actually be having a counterclockwise rotation, because you would be putting your left thumb in, and that's going to go in the opposite direction, in the counterclockwise direction, whereas our positive charge would be rotating in the clockwise direction. If my charge was instead coming out of the page, and it was positive, my thumb would point out of the page, and that would cause me to have a counterclockwise. So that's pretty easy. Put your thumb in the direction of the charged particle if it's positive. Right hand rule. If it's negative, use the left hand, or just know you have to flip the direction. So our magnetic field vectors are straight lines. They're always going to be tangent to the magnetic fields, and they're going to be weaker the further away that you get. So my field vectors are always going to be tangent to the circle, and they're going to decrease in strength. And that just makes sense. That's true for all of our fields. So the further away you get from the source, the weaker it's going to get. Now, how do we know how strong it's going to be? And how does this relate to currents? Because we've just talked about charges, but what about currents? So there's a law that's called the Biot-Savart law. It's French. I don't speak French. I apologize. And it is a calculus-based law. So this is an integral. It basically means sum. It means you add up the little pieces. That's what an integral is. There's a lot of things in here. That's our permeability of free space. We have our current. That's really important there. There's this little thing, dl. dl is basically a little section of length vector. It's the little dl means infinitesimally small. Well, if you take a current that you know is made of a whole bunch of moving charges, if you go smaller and smaller, and I take smaller and smaller pieces of this, then eventually you get down to a single charged particle. So this little dl is basically like a single charged particle. And then there's this cross r hat, and that's really kind of confusing because this r hat thing is like this unit vector, And it gets really crazy. Trying to figure this out and make sense of this is just weird. But what it basically says is a current carrying wire with a current of I, when you break it into tiny pieces, acts like moving point charges. Well, we knew moving point charges create looping magnetic fields. So what's going to happen is that current carrying wire is going to create a looping magnetic field. And if you pick a point that it is some radius from the wire, you can calculate the magnetic field. Now, we are never going to use this. But if you were taking a calculus-based course, you would use this equation and you would solve for the magnetic field at any radius r from that current carrying wire. And so that's what we're going to look at without the calculus. So we're going to assume that someone way smarter than we are, or at least that has way better math than we do, has gone through the effort and they've used the Biot-Savart law for a long straight wire. And what they found is that the magnetic field due to a long straight wire is equal to mu naught, the permeability of free space. It's kind of like E naught when we were doing Gauss's law. So it basically says how well do our magnetic fields permeate free space. Free space is a vacuum. It's a constant on your formula sheet. It is 4 pi times 10 to the negative 7th. Tesla's meters per ampere. So don't have to memorize that. It's on the formula sheet. I is our current. So if there's a current flowing through the wire. And then it is based on the radius r. So how far are you? So your magnetic field is creating loops. So if I put my thumb up towards the top of the page and I curl my finger around, I'm going to get a loop here that is in the, what is that? That's the counterclockwise direction because my current is going up. And then at any particular radius, if I pick a radius here, r, that is the magnetic field strength. If I pick a radius that is twice as far out, and I look at this r, because my r is in the denominator, my magnetic field is going to be weaker. A bigger r is going to give a weaker magnetic field. In fact, if I have 2 times the r, I'm going to get half of the magnetic field. Now, current is on top. So if I were to have 2 times the current, I would end up with 2 times the magnetic field. And that formula is on your formula sheet. There's going to be a lot of formulas that look like this. You do have to know which is which. So a long straight wire is mu naught I over 2 pi r. So that is our first example. And there's some other example videos linked in the lesson content for how to use these different formulas. And we're going to look at an example here in a minute. So the magnetic field is not constant. It gets weaker the further you go from the wire. But at any fixed distance r, the magnitude is constant. So the magnetic field is a vector that's tangent. So at different points, I'm going to have different directions of my field. But it's always going to have the same strength at any radius r. Now, how do you find the direction? So we use the right-hand rule. That is the curl right-hand rule. That's what I usually call it. And we do it kind of like what we did with the moving charge. What I picture doing, and I have a video that walks you through the different right-hand rules for wires, is notice that you put the thumb in the direction of current. So your thumb is going in the direction of current. But the other thing I do is I picture actually holding the wire in my hand. And that's kind of what that shows. If you hold the wire in your hand and my thumb goes along the wire, when I curl my fingers, that's going to give me my direction. But at any one instant, the actual magnetic field vector is a straight line. And so if you see those field vectors are always perpendicular to a radius. So if I was to draw the radius here, they're always going to be perpendicular. So your magnetic field is perpendicular, tangent to the radius. And so you look at any point. So in this case, we've got a current that's coming out of the page because it's got the dot. So when I put my thumb up and towards the top out of the page, then my fingers curl around. So my magnetic field is creating counterclockwise loops. But at any one instant, I'm going to have a magnetic field. And I can see that I drew those vectors smaller the further away you go. So you're going to be strongest really, really close to the wire, and you're going to be weakest far from the wire. If you flip the wire, the magnetic field's still going to loop, but it'll be looping in the opposite direction. And here, as remember, when we use capital I, we are talking about conventional current. So it's like moving positive charges. Got the other, conventional current. So it's as if we had positive charges that are moving. And we can see that in the simulation. So if I was to switch to a current line, so the yellow here is my current line in there, and I can see that that magnetic field is creating loops. If I create a little more vector density, maybe we can see. No, it doesn't really help there, sorry. But you can see that we are getting those looping magnetic fields. Those are the vectors. And then if I draw the field lines, you're getting those same loops. So that's the same kind of effect that we had. And then you've got your current that is moving. So we're getting those looping magnetic fields. So when we take a look, one of the most common examples we're going to see is parallel wires. So in this case, we have pairs of parallel wires. In the case on the left, the currents are flowing in the same direction. In our example on the right, the currents are flowing in opposite directions. So what happens is that if you were to run really, really large currents through, they have to be huge currents, that you would find that if you have straight wires with large currents going through, that those wires are actually going to attract to each other. And I'm going to put some links to some demonstration videos into the set of lecture videos that you're going to watch, so you can see that demonstration, that it actually happens in real life. And so those wires are going to be attracted together. Now, if you were to observe the ones with currents flowing in opposite directions, they are going to attract. And the forces are equal and opposite, because Newton's third law says that the force of one object on another object have to be equal and opposite. So how do we find that? So if we want to find the force between the two current carrying wires, in this case we have I1 and I2 going up. They're separated by a distance d. The length vector is in the same direction as I, and the length of these two wires is the same. So what happens is, if we look at wire 2 over here on the right is creating a magnetic field. I'm going to call it B2. This is the magnetic field created by wire 2. So if I put my thumb towards the top, I know that it's making a counterclockwise loop. So, but at the exact location of I1, I've got a dot here, because that loop is, if I was to put my thumb on wire 2 right here, and I was to then curl my fingers around as if I was holding wire 1 in my thumb, my fingers actually point up out of the page at that instant. So although I'm making a looping magnetic field, at this instant, the magnetic field where wire 1 is located is directly out of the page. So that's going to be important, because that's just the magnetic field. So the magnetic field, we used was mu naught I over 2 pi r. That came from the Biot-Savart law for a long straight wire. But it's I2 because it's the source, and the separation distance is d. That's basically the radius of this loop right here is equal to d. So if I wanted to find the force, this is the force of a magnetic field acting on a long straight wire. Well, we know that our force is going to be based on IL cross B. And of course, these are perpendicular, because going towards the top of the page for I1 and out of the page for B2 is perpendicular. So I don't really need the cross product. It's just going to be ILB. But I have to be really, really careful that this is the force of the magnetic field from wire 2 acting on the current I1. So you have to be really careful with your subscripts. So we don't need the cross product because it's just going to be ILB. And if I use my right-hand rule, I can, for that cross product, I can figure out the direction of that force. So the cross product right-hand rule says I put my fingers in the direction of L. Well, this is for wire 1, so that is towards the top of the page. So that L is also in the direction of I1, so towards the top of the page. I then rotate my palm, so fingers here, and then I rotate my palm so that it is facing B2. So my fingers go in the direction of I1 towards the top of the page, which is the same direction as L. My palm has to face B2. With my fingers pointed towards the top, B2 is pointing out of the page. So that means my palm has to face out of the page. That causes my thumb to go to the right. So that's why our force of wire 2 acting on wire 1 points directly to the right. So that is an attractive force. So if you simplify the cross product, because they're at 90 degrees, you just get ILB, but it's I1LB2. And then what you do is you take B2 and you substitute it in here. And when you do that, you get the force of wire 2 acting on wire 1 is equal to I1L mu naught I2 over 2 pi d. And a lot of times they rearrange this, and so this is what it was going to look like. That's what that force is going to be. Now we know that that force of 2 on 1 has to be equal and opposite to the force of wire 1 on wire 2. So I can predict that the force of 1 on 2 has to be in the opposite direction. So that those two forces are going to attract, and those two wires are going to come together. But we could also show it. So if we do the opposite wire, so now we're starting with wire 1 as the source. So wire 1 is now the source of our field. So if I put my thumb in the direction of I1 and I curl, and like I said, I put my thumb and I pretend like I'm holding wire 1, my fingers are actually going to go into the page over on the right side of my thumb. So my magnetic field due to B1 is going to be directly into the page. So we're going to go the same process because that magnetic field for 1 is going to be the same. It's going to be mu naught I1 over 2 pi d because the radius here is equal to d. We're still going to use that our magnetic force of object object 1 on 2 is going to be, in this case, current for wire 2 L cross B2, or B1, sorry, because it's B1 is going to be our source. So B1 comes here. You would put your fingers in the direction of L, which is in the direction of I2. So that's going to be to the top of the page. I keep my fingers straight. And then I rotate my palm so that it faces B1, which is into the page. So my fingers towards the top. B1's into the page. My thumb points to the left. So I can see that those are going to be attractive forces. And if you plug in and do the math, what we find is that if we sub in, we get that our F of 1 on 2 is equal to I2 L times B1, because we can ignore the cross product since they're perpendicular. Sub in for B1, we get F1 on 2 is equal to I2 L mu naught I1 over 2 pi d. Sorry, I got a little bit of a delay here. So, and then if we rearrange, what we end up getting is the exact same thing. F1 on 2 is equal to, if I go back and look, make sure it's in the same order here. mu naught I1 I2 L over 2 pi d. Same idea. Mu naught L I1 I2 over 2 pi d. So those forces are equal and opposite. Now, if you were to use the same right-hand rules for the forces themselves are going to be the same magnitude because we have the same currents, we have the same distance, but the direction is different. So if, for example, we are using, I could have sworn it was there, we're going to use I1 as the source again. Then our source of our magnetic field is creating a looping magnetic field. So we're going to get that looping magnetic field right here. So now if I put my thumb towards the bottom of the page, when I'm over here at wire 2, instead of being into the page, I'm going to be out of the page. So B1 is now out of the page at the location of that wire. And so what that ends up doing is when we do that, our force of wire 1 on wire 2 is equal to I2 L cross B. That B is now B1. That's the one that's our source. So I put my fingers in the direction of I2, which is towards the top of the page. Now my palm is facing out of the page. My thumb now points to the right. So the force of wire 1 on wire 2 points to the right, and then the force of wire 2 on wire 1 points to the left. So those are now repulsive forces. So I do suggest you take a look at the video that shows that the wires do actually move in those directions. Kind of fun. So now, what if instead of a long straight wire, we have a loop? So this loop is actually cutting into a paper with iron filings right here. So you can picture that this loop goes through the page and comes out. So you're making a current loop. So this current loop is connected somehow to a power supply that is going to allow it to go to rotate. What ends up happening is what the loops are usually not like 100% perfect. They connect to a power supply, kind of like that. So they're not 100% circular loops, but the idea is still there. It's the same. You got that current loop. So what we end up getting is something quite different. We get that our magnetic field loops around the loop. So actually, if you go through the center, it's kind of straight, but you can see that we're creating loops of magnetic field here around those wires. So that's kind of what this looks like. A solenoid is a really, really important tool. There's one in your car as part of the alternator, I believe. And solenoids are used in a lot of electric circuit applications. And so a solenoid is basically a whole bunch of wire loops kind of all connected together. So if we start with a single loop, we can then build up to a solenoid. So here's like a view of the magnetic field lines. So as I mentioned, the field line is going to go pretty straight through the center right here. But then all the other field lines are going to loop. So you're going to get this looping magnetic field. You could solve this from the right-hand rule if you were to look at the current. So the current here is coming out of the page. So if at that one instant I was to put my thumb out of the page, I can see that I'm going to make little loops. So and those little loops are going to be counterclockwise with my thumb coming out of the page. Well, picture that current comes up out of the page and goes into the page on the other side. So we have into the page for a current here. Well, if I put my thumb into the page, that's going to create a looping magnetic field. That is in the clockwise direction this time. So we can use our same rule for magnetic fields for the long straight wires to find that right-hand rule there for that. So, but what we can do is we can actually look at what's going on at the direct center. So the direct center of these loops is often what we are the most interested in. And so if you curl your finger around the loop, where your thumb points is where the magnetic field is going to point for that loop. So here's an image of that, okay, of that right-hand rule. So this is another curl right-hand rule, but in the previous example, when we had a long straight wire, our current is what was straight, and so we got looping magnetic fields. So if I put my thumb up, I'm going to get that looping magnetic field that is going to be in the counterclockwise direction. Here instead, what you're doing is you're curling your hand, your fingers, so that it follows the current. So if you curl your fingers so that it follows the current, your thumb points in the direction of the magnetic field inside the loop. Now we know that that field is going to then curve, so it's going to curve out and around. It's going to curve out and around, but inside the loop, we can curl our fingers around the current, and then our thumb points towards the top. Now, this has a very similar equation to a long straight wire. The long straight wire was B equals mu naught I over 2 pi r. You could use the Biot-Savart law to derive this with calculus. We don't have that, so we just know our formula. So this is on the formula sheet, but you have to be very careful with it. So this one is very similar, it just doesn't depend on pi. And it is the field at the direct center of that singular loop. If you had multiple loops, so say we had a bunch of loops stacked on top of each other, so if I had loops stacked on top of each other, then what ends up happening is you basically add all of those magnetic fields together. And you would get N times mu naught I over 2R, where N is your number of loops. So if you could picture kind of like bangle bracelets, or like stacked hoops, washers or something like that, if you were to stack those on top of each other and somehow give them a current by connecting them to a power supply, that's what you would end up getting. So each loop stacks on top, and they're each going to be creating a magnetic field that adds. So that's why you multiply by the number of loops. Now this is kind of like a solenoid, except for instead of stacking loops, a solenoid uses a single piece of wire. So instead of individual loops that are closed, we have a wire that loops around. So they often put this like around like a hollow tube, and then you wrap the wire around the hollow tube. And so what ends up happening is when you look in the center of the solenoid, ignoring the edges, we get a very uniform magnetic field. That is one thing that makes the solenoids really, really useful, because inside you get this uniform magnetic field. So if I'm doing research, I could create a huge solenoid and then create a uniform magnetic field, constant in magnitude and direction inside. What's so cool about this is that it's uniform. It's not dependent on the radius. So this is the formula for a solenoid, and you can see that there's no R in here, so that the actual radius or diameter here, if this is our central axis, the radius here does not matter. So if I pick a spot here close to the wire or further out around over here, no matter where I pick, the magnetic field is going to be the same everywhere. So if I want to talk about the strength of this magnetic field at the center, it's uniform, so it's based on mu naught, the permeability of free space, so that's that constant. N is once again our number of loops. So if you were to count up those loops here, this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 loops. Okay, so we got 10 loops there. I is the current that's running through the wire, so that is our current. And L is the length of the solenoid. So L is our distance from the last loop to the first loop. That's our length L. Sometimes you'll see this formula written instead like this: B equals mu naught N times I. So if you see it written like this, N is just N over L. They call this turn density. It's our turn density. It's the number of loops per unit length. So the idea is the more compact those loops are, so if my loops are tighter together loops is going to create a stronger magnetic field than our loops that are spread further apart. The bigger the current we run through it, the stronger the magnetic field is going to be. So then how do we find the direction that the magnetic field is going to point? So there's another right-hand rule. So once again, I have a video that kind of summarizes all the right-hand rules for current carrying wires. So what you do is you look at where the current is flowing. So I start with the current that is coming into the solenoid, and then I picture wrapping my hand in the direction of that current. So this hand is wrapping up and over the top because it's tracing this wire. So it's going up over the top and behind. Now where the thumb points, that's where the magnetic field is going to be inside. So when you're inside, that is where your magnetic field is going to be. Now that magnetic field is going to leave over here and come back around like this. If I look, the one next to it's going to come out and around and cut back around like this. So what ends up happening is, remember that our field lines leave the north side of a magnet and enter the south side of the magnet. So picture that this is really close to the magnetic field that's being created by a bar magnet. So if this was a bar magnet instead of a solenoid, we would have the north side of our magnet over here. Oops, sorry. The north side of the magnet on the left and the south side on the right. So you can curl your fingers around. Notice that if I were to have a compass, that was one thing we talked about, is using compasses to track field lines, that compass would actually point in the opposite direction outside, as if I could put that compass inside that tube, that compass would point from right to left, but outside it points from left to right. So that if I was to actually look down the central axis of that tube, what would end up happening is my field on the inside would be in the exact opposite direction as the field outside. And that's true for a single loop or for a solenoid. Okay, that what's going on inside the loop is going to be opposite of what's going on outside. And this right-hand rule gives you what your field is doing inside. Okay, it's the direction inside is what this right-hand rule gives you. So the magnetic field is pointing towards the left here. So what direction would the current have to point to create this magnetic field? So if that is my magnetic field into the page, what I could actually do is I could put my thumb into the page and then look where my fingers curl. And my fingers, to create that, would actually have to be curling in the clockwise direction. If my fingers curl in the clockwise direction, my magnetic field inside is into the page. And on outside the loop, it's going the opposite direction because it loops back in around on itself. So there is an example problem in the videos that shows how to solve problems and do calculations with solenoids. So our very last topic is Ampere's law. So this is going to be another thing that is going to be more calculus intensive. Think back to Gauss's law. So Gauss's law basically said that our magnetic flux, which we could approximate our flux, is like E times A is equal to our Q enclosed over our E naught. Okay, as long as our E and our A were parallel to each other. Okay, similar idea here. There's actually an integral for Ampere's law that says if you were to create an integral, a closed loop here, B dot dl, that's equal to mu naught I enclosed. Well, we don't really know how to do this side of it. But as long as we are looking at what we call an Amperian loop, Instead of a Gaussian surface, we're looking at an Amperian loop. We look at a closed loop in space, and we make it symmetrical around our wire. So we make a loop here. This loop doesn't exist. This is a long straight wire here, for example, and my loop, my Amperian loop, is enclosing that wire. Now I've chosen this wire so that it is symmetrical to the magnetic field, because I know that that loop is making magnetic fields that are looping around, in this case looping around in the counterclockwise direction. So if I were to choose a loop of length L, this is the length of the loop, not the wire, the length of the loop. Well, the length of this loop, sorry, there's a red there. The length of this loop here, the length of that, well, that's the circumference. The circumference is 2 pi r. So if my length of my loop is parallel to my magnetic field, because I've chosen a loop that's symmetrical to my magnetic field, then the product B times L is equal to mu naught I enclosed. So this would actually allow us to find the magnetic field of a long straight wire, for example. Because if I were to divide by length on both sides, I would get B is equal to mu naught I enclosed over L, but L is the circumference, that's mu naught I enclosed over 2 pi r. If you rewind, that is the magnetic field due to a long straight wire. Well, Ampere's law can apply, and we can solve in those equations that I gave you for a single loop. B is equal to mu naught I over 2r. Or for the solenoid, B is equal to mu naught N times I over L. All of these can be derived from Ampere's law. So Ampere's law would be used by students in calculus-based courses to derive the equations for magnetic field. It's used similar to the Biot-Savart law, but Ampere's law requires symmetry. Okay, so it requires you to have something symmetric. Now, you're not going to be able to do much with this because of all the assumptions that we have to make to use it. But one example that you might see is when you have like multiple wires. So let's say I have a loop here, and I have a bunch of different wires. I have like I1 coming out of the page, I've got I2 going into the page, and I have like I3 maybe coming out of the page, and then maybe over here I have like I4 out here, and then I have like into the page I5. It doesn't really matter. If I was to try and use my magnetic field for a long straight wire, this would get really, really complicated, because I'd have 5 different wires and I'd have to find all those distances. I'd have to be using my mu naught I over 2 pi r over and over and over again. And that would be a lot of trouble. But if this is an Amperian loop of length L, then what this says is that my magnetic fields due only to the currents that are inside that loop. So that means that the currents here, I5 and I4, are not contributing to the magnetic field inside that loop. And if I assume that like these 3 wires are really, really, really tightly packed, so for example, they were all here together, then that loop is at the same kind of distance r from the center. So the magnetic field, if I wanted to find the magnetic field here at B, what I'd have to do is I'd have to find my I enclosed. Well, if I assume that my I enclosed is going to be the sum of those, I would take I1 and I3 and add them together because they're both pointing out in the positive direction, and I would subtract I2. So this would allow me to find, in a really simple way, the magnetic field if I knew the length of my loop that I chose and it was symmetrical around the center of those wires. I could find my magnetic field strength. Now, you won't do too much with that. It's more of a conceptual application for you guys. It's just understanding that this is actually a fundamental law of magnetism.